Alrighty, folks. So up to this point, we've been discussing and defining various things related to motion. We've talked about position, we've talked about velocity, and acceleration. And now we're going to start looking at the relationships between these things. We're going to start looking at plotting, and then we'll consider some equations, and eventually we'll start working some examples. And I hope to get a good opportunity to allow you to do some examples on your own as well. All right, so let's begin with something called a motion diagram. And a motion diagram is pretty much exactly what it claims to be. It's a diagram that aims to illustrate something's motion. And what I want you to sort of imagine is like a strobe light or snapshots of something. Imagine taking pictures in equal amounts of time, equal increments of time. And so you get these snapshots, call it every 1 second, millisecond, whatever you wish. And then you can see where something is at that instant. And now the relation between these individual snapshots can tell you something about that object's motion. So for instance, let's look at this little motion diagram. It's of a ball moving across a table, let's say. And our first snapshot, the first camera click, it's here, then here, 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 here. And what you might notice about that, I've drawn it to the best of my ability, is equal spacing. That after each amount of time, this ball has moved an equal distance. Now, if it's moving the same distance in the same amount of time, it must be moving at the same rate, have the same speed or velocity. In this case, we can see it's moving to the right. We could give it direction. This is a motion diagram for constant velocity. And equal amounts of time, it moves equal distances. It's covering the same amount of distance, or it has the same amount of displacement in equal time intervals. That means it's moving at a constant rate, a constant velocity. Well, alternatively, we could have a picture that looks something like this. Well, in this image, we can see the ball starts, covers an amount of space, and then it covers a little less, and even less, and less, and less. There are decreasing spacings between these images. It's covering less space in equal amounts of time. So it must be moving faster here, but if it doesn't go as far between these timestamps, it must have slowed down. And then it slows down more and more and more until if it was stopped, we would just keep piling up images right on top of the other. This motion diagram indicates a negative acceleration or deceleration. We can see from the decreasing spacing that this object is slowing down. And the flip side of that would be something speeding up. So I've tried to draw that here as well. We can see that this thing is moving not very far in this first timestamp, but then it makes up more ground in that timestamp. It goes further in the same amount of time, which means it must be going a little faster. And then it goes even farther in the next timestamp, and farther and farther. And so we can see that its speed must be increasing. It's accelerating. That acceleration must be in the same direction as its velocity. It's moving to the right and being accelerated to the right. It's speeding up. And to add upon that, in our previous motion diagram, it must be moving to the right, but experiencing an acceleration to the left to be slowing down. So that's the basics of motion diagrams. They're like watching a strobe light on an object, and where those images are can tell you some information about the motion of the object. Specifically, we're going to look for situations that are constant velocity, equal spacing, or some form of constant acceleration, either decreasing or increasing spacing. But in either case, we see changes in those increments, and that indicates some form of acceleration. All right, now let's talk a little bit about graphing. So we've got a graph here of position versus time. And I ask, what does this show? Well, I've labeled this graph, so we can take a minute to look. I've labeled this as position on the y-axis, and I've labeled its units as meters. And I've labeled time on the x-axis, and I've given it units of seconds. And we would refer to this as position versus time. How position changes as time goes on is a good way to interpret this. Well, let's think back to our algebra roots. If this is a line on this graph, we have y equals mx plus b, must be some form of the line. And if you will recall that m represented slope. Slope is computed as your change in y over your change in x, or most teachers explain this as rise over run, how much your vertical amount changes as your horizontal amount changes. Well, if we consider our y coordinate, we've got position on our y-axis. Change in y is given by change in d. That is the letter that we use to describe position or displacement. So we have displacement as our change in y-axis, and on the x-axis we have time, change in time. Well, we've actually looked at this already, this chapter. Change in position over change in time, or displacement over time, gives us velocity. Velocity is the slope of this graph. Velocity is the slope of a position versus time graph. And if you didn't notice that from this sort of definition chain of thought, you might notice it from the units. If we look at the units of our slope, change in y over change in x, the units of y are meters. The units of x are seconds. We get units of meters per second whenever we compute the slope. And meters per second are the type of units that go along with velocity. All right, now, there are a series of rules we will cover for position versus time graphs. These are always true whenever you plot position versus time. First, if you have a straight line, that means you have a constant velocity. A straight line has the same slope everywhere, and we already said that the slope is velocity. So if the slope doesn't change, the velocity doesn't change. In other words, it's a constant velocity. The steepness of the slope indicates the magnitude of velocity. If your slope is very steep, and we can peek back at this plot, if it's steep, then you're going way up. You're changing your position very rapidly, which means you have a large velocity. And similarly, if it's not very steep, you're changing your position slowly. It's a low velocity. Next, the sign of your slope indicates the direction. And then we have magnitude and direction here to define our velocity. If you have a positive slope, it indicates forward motion. Positive, you're going upward. Your position is increasing in value. A negative slope, your position is decreasing in value. So a positive slope indicates forward motion. A negative slope indicates backward motion. Next, a curve would indicate a change in velocity. A curve, or potentially just an angle in that graph. Basically, if your slope changes, well, slope is velocity. There must be a change in velocity. And lastly, this is a special case of the first rule, but if you have a flat line, that means your velocity is zero. Your position is stopped. A flat line, you're at some position, and it's not changing as time goes on. You're at 3 meters, and that doesn't change. You continue being at 3 meters. And that's still a constant velocity. It's just a velocity of 0. All right, well, that would be for position versus time graphs. We're also going to plot velocity versus time. So let's see some of the subtle differences between velocity versus time graphs and position versus time graphs. They're going to have a lot of similarities, but there will also be some very crucial differences. So here you can see I have plotted velocity on my y-axis, and I've given it units of meters per second. And I've plotted time on my x-axis in units of seconds. And again, I ask, what does this show? Well, we've got a straight line. Let's think about what information can come from that straight line. Again, we can find its slope. The slope m is change in y over change in x, rise over run. Well, change in y is a change in velocity. Change in x is a change in time. And if you'll recall, the definition of something's velocity changing over some amount of time is acceleration. Acceleration gives the slope of a velocity versus time graph. And again, we can show this not only through the definition of the variables, but also through the units. If we consider the units of the y-axis, they would be meters per second. And if we consider the units of the x-axis, they are seconds. Meters per second, well, that sure sounds like how your velocity is changing, or meters per second squared, what we would expect the units of acceleration to be. All right, and now to finish off this video, let's look at the rules for velocity versus time graphs. They're very similar to the rules for position versus time graph, with just a couple of words substituted. For instance, now if we have a straight line, well, that line, if it is straight, only has one slope. Slope is the acceleration. So if it's a straight line, the slope is always the same, which means the acceleration is always the same, or we have a constant acceleration. Similarly, the steepness of that slope indicates the magnitude of acceleration. If it's very steep, you're changing that velocity very quickly. If it's shallow, you're changing that velocity slowly. Also, the sign of the slope indicates the direction of the acceleration. A positive slope is a positive acceleration. A negative slope is a negative acceleration. And of course, you can then compare those to your velocities to determine if you're speeding up or slowing down. Remember, if velocity and acceleration are in the same direction, you speed up. If they're in opposite directions, you're going to slow down. And lastly, a flat line indicates acceleration of 0. If you can imagine a line straight across from here, say at 2, a velocity of 2 meters per second, well, we're at 2 meters per second, and we're just staying at 2 meters per second if we have a flat line. If your velocity is not changing, that means your acceleration is 0. But there's a little bit more information that you can get out of this graph. If you have a flat line, that means acceleration is 0, but if you know the acceleration is 0, that also tells you your velocity is constant. So there's a little bit more information to be had when you have a flat line in an acceleration, in a velocity versus time graph. All right, now I think we'll leave it for there. We'll look at these one more time and then consider some of the equations that will go along for these things, as well as one good source of acceleration that we can always count on. I'll give you a hint. It's what happens whenever I drop my pen. All right, we'll see you next time.